So this is the Wolfram Alpha widget that's going to solve our complex equation for us. As we saw, we have this complicated expression, 4 minus 2x squared over 3x cubed times x is equal to 0.121. We can go ahead and plug that in to our widget. So all we need to do is go ahead and plug it all in. So we have 4 minus 2x. We're going to have to square this entire expression. So this is the pain in the butt part. We have to learn how to use the syntax here. And over this we're gonna have 27x to the 4th power. And let's just go ahead and put parentheses around that just in case. That's 3x cubed times x equals 0.121. We simply need to click solve. We're going to get a pop-up window that's going to go ahead and give us our values. We don't need to have all these crazy actual things. We're going to use this approximate forms, which will give us actual values. As we can see here, we have 3 values that don't make any sense. We have 2 of them that are imaginary numbers, so forget those. We have a negative value, which doesn't make sense either. And we have a positive value. That's the one we're looking for here. So because we had an x to the 4th expression, we will get 4 x's that work out. But we have to think what ones make sense. No imaginary numbers allowed. No negative numbers allowed either. All right, and so we're going to see that x is 1.0339. So if we hop back here, and my thing decides to disconnect, as it should, once we have this value, we just need to plug it in for our x's. So we found that x is 1.0339. I hope. Let's just go and double check that. So yes, 1.0339. Remember, this negative value doesn't make sense because we saw here, well, we have 0. If we had a negative x, we can't have negative nitrogen. That makes no sense. So x should always be a positive number. And so, generally speaking, you should only find one that works. Of course, we can't have x be bigger than 2 either. So you just have to think about it rationally, right? If 4 minus 2x is one of our values, x can't be more than 2, because we can't possibly have a negative concentration of ammonia either. And so, in this case, we figured out that x is 1.0339 atmospheres. Our equilibrium expressions are here. So we saw that the pressure of hydrogen is 3x. And so that'll be 3 times 1.0339. Let's calculate that. 3 times 1.0339. We get 3.10. And that'll be atmospheres. For nitrogen, it was simply x. So it's 1.03, we'll say, atmospheres. And then the ammonia was 4 minus 2x, so 4 minus 2 times 1.0339, which will equal 4 minus 2 times 1.0339, 1.93 atmospheres. So we have our equilibrium pressures of each component of this reaction. And we get that using the ICE table. So our ICE table overall, we started with our initial concentrations. We went ahead and saw our changes using the coefficients of the reaction. We know that we have products, so those products are going to break down. We saw that we don't have reactants, so we're going to need to make those reactants. And once we have that, we can set these variables, the 4 minus 2x, the 3x, and the x, into our equilibrium expression, which we have a numerical value for, the 0.121. That's given to us in the very start of the problem. We can solve for x. Please use a calculator. Don't try and do this manually. Solving for x to the 4th is incredibly difficult to do by hand. Please use a calculator. I'm going to go ahead and link that widget I used in Discord for us, and I'll put it on Canvas too. So we calculated our x, we picked the value of x that makes sense of the 4 options we had, and then we plugged in our equilibrium line, the E line of our ice table. And now that we've done that, we have our equilibrium pressures for this system. So we see that some of that ammonia has broken down. We've produced hydrogen and nitrogen as a result. And so we'll be doing this a lot. Again, we can use concentrations as well. In this case, we had Kp and we had pressure values. Remember that you can also be given either reactants or products. Equilibrium works both ways. If you're given products, that product is going to break down to form reactants. If you're given reactants, those are going to combine to form products. So it doesn't matter what you start with. The important part is you know which one is going to be negative, which one is going to be positive. In this case, we had products, so we're going to be losing products as we approach equilibrium. We did not have reactants, so we're going to be making reactants as we head towards equilibrium. Lots of math, but thankfully the hard calculation is done for us using a computer. In our next video, though, we're going to take a look at how do we know if we're not given 0 to start. How do we know which way the equilibrium will go? If instead of having no hydrogen and nitrogen and only having ammonia, what if we had some of each? How do we know if the system is at equilibrium? Or is it in a position that's going to be making products? Or in a position that's going to be making reactants? That'll be in our next video.